So for this question, we have this fluid going down between this wall or plates, and this 2h width. Gravity is acting downward. This is our coordinate. This is x direction, and this is where the 0 is in the center line. And it's going down into z direction. And you can expect that the fluid velocity profile for this fluid will be something like this. And this is fully developed and is not a pressure-driven system. First, we have to determine whether it is a rectangular or cylindrical coordinates. And obviously, since we're not using any radius, we know this is a rectangular coordinates. So among these two, rectangulars and cylindrical, we can choose this rectangular. And along rectangular, we have three forms, whether it is Vx, first one, Vy, or Vz. So that represents how the fluid is moving. And we see the fluid is moving downward, so into the z direction. So what we're going to choose among the rectangular coordinates is the third one, Vz. And that is what I have on this paper. And as usual, our left side all cancels out because it's fully developed and it's all one directions. And on the right side, we have these. And this, because this is not pressure driven, dp over dz goes to 0. We are moving to the velocity will change by the x coordinates, right? And so even if the fluid is over here and here, so their z directions are different, but their velocity is going to be the same. So this one goes away. And the y direction, well, there's no really y coordinates. So because this is one directional, it goes away. And our density times gravity constant, gravitational acceleration, we have gravitational acceleration acting on here, so we're going to keep this one. So what we have left is on the left side is completely 0. The right side we have this one left. We're going to solve it out. We're going to move this term to the left, and then we're going to divide it by mu, and then we can take integral on both sides, and what we will have is over here. Actually, this we don't need 2 over here. We just need x. And then, we just need x plus c1. I'm going to change the rest of it. And we take an integral one more time. It's going to be 2. And then c1x plus c2 equal vz. This is 2. So I'll just put it on to the right side. Switch this place. And now that we have here, what we have to do is using boundary conditions, we can figure out c1 and c2. We know over here at this maximum velocity at the very center line, we know that. And we also know that at this point, the change in velocity is 0 at this very center line, because that's just a simple calculus. So dvz over dx at x is equal to 0, because it's at the center line, it's going to be 0. The change in velocity will be 0, and that is, yep, that's correct. And I got this dv or z over dx got from here and from this process. So there should be no 2, actually. So it's when x is equal to 0, this whole value is equal to 0. So we know c1 is equal to 0. And then second boundary condition, when x is equal to h, so at this wall, because this is 2h, at this wall, we know the velocity will be equal to 0. So I just plug this over here. I'll change it into 2. And when x is equal to h, this is going to be equal to all this h squared plus c2 is equal to 0. And that gives us the c2 is equal to density time over 2 mu, which is viscosity, gz, which is gravitational acceleration, h squared. And putting this c1 and c2 back into this vz, we'll get something like, change it into 2, okay, something like that. And we can further simplify this. Mu over 2, density rho over 2 mu gz h squared minus x squared is equal to vz x. And that is our velocity profile of this system.